Hi, everyone. This is Aaron Larson, Executive Editor of Power Magazine, and you're listening to the Power Podcast. On today's episode, I'm joined by John Olav Tande. He is the Norwegian Chief Scientist at SINTEF Energy Research. Mr. Tande, thank you for joining me, and if you don't mind, please tell a little bit about SINTEF Energy Research and what you do there.
Yeah, thank you for having me at this podcast. Well, SINTEF Energy Research is part of the SINTEF group, and the SINTEF group is a number of research institutes working within renewable energy and technology for a better society. We are about 2,000 researchers at SINTEF, and at SINTEF Energy we are about 250, and we address then in particular energy research. For me, I'm a chief scientist at SINTEF. I've been working with offshore wind since the start, you could say, and I've been specializing on grid connection and offshore wind farm control systems and these kind of technicalities. Also been working with land-based wind before that, and I've had a long and productive career within wind energy.
Wind energy, is obviously very important to the energy landscape right now. I know in Norway you have a lot of offshore wind and a lot of other wind resources that you're using. So can you talk a little bit about the intricacies or differences between onshore and offshore wind?
Land-based wind turbines and offshore wind turbines work in a similar manner, in the sense that they both have a turbine that rotates because of the wind. And this turbine drives a generator that produces electricity, and this electricity is fed into the electric grid system and transported to end users. Then offshore wind turbines are obviously at sea, and they can then be bottom fixed, so they can stand on foundations that are fixed to the seabed, more or less as on land, just that you have sea in between, or they can be floating. And if they're floating, they can float more or less like a boat, if you can imagine that, but more or like a buoy. And if you consider a spar buoy, this is well known from the oil and gas business, and you can fix this to the seabed then with mooring lines and anchors, and then it will stay in position and float freely in the water, moving with the sea, but at a fairly fixed position geographically. The other alternative is to have semi-submersible platforms. These are platforms which are not going so deep that the spar buoys, but also float freely in the water. And these can be used at more intermediate water depths, like 50 to 150 meters maybe, and the spar buoy can go for 100 to 300, 400, 500, 600 meters water depth.
That's quite deep and really opens up a lot of additional territory where these wind turbines can be installed. Actually, in Power's September issue this year, one of the top plants that we talked about was the Wind Float Atlantic project, which is off the coast of Portugal, which has floating platforms that are used for 3 big wind turbines that are 8.4 megawatts each. Can you explain any research that or new testing that you're doing, particularly with offshore wind and these floating platforms? How do you see them changing the landscape for wind energy?
Yeah, so you can say that the platforms that are used, they as I explained, they can be semi-submersible, they can be spar buoys, and there can be alternative platforms also. And this is a very visible difference from bottom-fixed turbines or onshore turbines. And of course, to start with, well, the first floating wind turbine in full scale was installed in 2009. Then there was very little experience with how to dimension this and how to sort of model the stability and keep it stable in the waves and winds and so on. And it was a lot of excitement when this first turbine was installed outside Norway. It was called Hywind, and installed by Equinor. And at SINTEF, we tested this concept in scale already in 2005, and the test was to figure out two things. First of all, if it could float stable in the water per se, and the other one was if we were able to control the blades, the pitching of the blades, so that it was kept stable in the water also when the wind speed increased above rated. And we managed to find a good way to control this, and this means that the turbine stands almost perfectly still, even if the wind is really high, and that means that it is not suffering a lot of fatigue. If it hadn't been for this control, it would have broken down by fatigue within a matter of weeks. So this is really a crucial element for floating wind, that we have this control system in place that reduces the motion of the turbine. Of course, you can reduce the motion of the turbine and the construction also by other means with ballast and so forth, but that adds costs and is, I would say, less of an elegant solution. At SINTEF, we do a lot of modeling work to improve the models we use to calculate how to dimension the platforms and how to keep them stable, including also the mooring system. And an improvement to these models can mean a lot for the cost of the final product. And this is something which we pay a lot of attention to.
I guess the cost is a big issue when you talk about offshore wind. It is quite significantly more expensive than doing an onshore platform. So how do you see that changing over time as more of these are developed and as they become more commonplace?
First of all, I'd like to say that offshore wind is maybe cheaper than you think. I mean, bottom-fixed offshore wind farms, they are today built without any subsidies. So simply competing on electricity price at the best locations. So the biggest wind farms that are built now outside UK, a Dogger Bank project, but it's competitive with the cost of electricity in the UK. Okay. Without any subsidies. So, but this is of course for bottom-fixed wind farms and very large wind farms. So these are built, in 3 wind farms, each rated 1.2 gigawatts. So these are quite huge installations. The floating technology, that is a much more new technology and less evolved, and there are only a few prototypes that have been installed. You mentioned the one from Portugal. There is a couple of others, but that's it. And the cost is, around about 1.5 Norwegian kroner per kilowatt hour. I have to translate this into euros per kilowatt hour, something if you like that. You divide it by 10. Yeah, so it's 15 euro cents per kilowatt hour. That's more or less the cost for floating, and for the cheapest bottom fixed is maybe 4 euro cents per kilowatt hour. So.
It's quite a substantial difference there.
Yeah, it's quite a difference. But this is not sort of for a physical reason or anything. If you look at the pure physics or the amount of steel, if you like, that goes into constructing a floating turbine and compare that with a bottom-fixed turbine, you'll find that the amounts of material that you spend are more or less similar. So it should be possible to produce floating wind turbines to the same costs as bottom-fixed turbines, and I would predict maybe even cheaper, because floating turbines you can install more easily. You can simply tug them out to the site and drop the anchors and hook them up to the grid, and then you have installed it instead of using piling and things like that to fix the foundation to the seabed. Also, floating turbines can be put at deeper sea, and 80% of the sea is deep. So 80% of the wind resource at the ocean is at deep sea. So you have a much larger area to locate your floating wind farms, and they can be located at more ideal positions related to wind resource, but also related to impact to other interests or environmental impacts or grid connection or fisheries or what have you. So there are possibilities to make actually floating wind to become cost competitive within the next decade, I would say, if we continue to do research and development in the phase that we are doing now.
Mm-hmm. At this point, what is the biggest cost to the floating wind turbines that makes it so much more expensive than the fixed bottom? It would seem that cost should be even closer if the materials that you're using are very much the similar amount.
Yeah, I think that the main difference is that for bottom-fixed wind turbines, you have an industry supply chain that has delivered a certain volume for some years, and there's been developed an industry supply chain that can sort of supply this in fairly large volumes. For floating wind turbines, it's still sort of I wouldn't say one-off, but close to one-off designs. And you haven't really built the supply chain yet. But once that is up and running, you will see reduction of cost. And also, of course, the technology is still not with the same maturity as bottom fixed, so there are opportunities to optimize the design and operation of floating wind turbines through research and innovation, and to make them cheaper also by that. So it's two factors, you can say. It's about developing the market to get the supply chain, and it's about research and innovation. And these two things will make floating wind cost competitive within the next decade or so, I would say.
Mm-hmm. And now a lot of the offshore wind turbines are getting bigger and bigger. I know Siemens came out with a recent, or Siemens Gamesa came out with a 14 megawatt unit, and GE has a 12 megawatt unit, and MHI Vestas has a large unit as well that they're working on. So how much bigger can these turbines get, and how does that change the potential for offshore wind?
Yeah, I'm almost tempted to say bigger is better, but there is some truth in that, because there are some fixed costs when you go offshore that are not really depending on the size of the turbine. So the cost of installation, the cost of the mooring system, the cost of the operation and maintenance, the cost of control systems and so forth is all fixed costs. So if you can make a bigger turbine on the same platform, it obviously makes the electricity from this construction cheaper than a smaller turbine on the same platform. And then with regards to how large these turbines can be, I think I would be cautious to sort of state some upper limit. I remember very clearly when I started in the wind energy business some 30 years ago, there was a very respected professor that thought that wind turbines would be about 500 kilowatt. That would be the sort of maximum size. And now they are, 20 times the size or more. And they're still increasing, and but of course, there is probably a limit, but we haven't seen it yet. And it depends on material, use of new materials. It depends also a bit on how you design the turbines, and we can also start thinking about multi-rotor designs and other types where you sort of increase the capacity at one platform.
Obviously, as research goes, there's always advancements, there's new technology, there's new materials, and so there's always things changing and improving. At your at SINTEF, for instance, what sort of research are you working on now? Is there anything that you feel could be game-changing down the road?
There are a few things. I would say game-changing is a big word, but in a recent research project we had, which I managed, it was a fairly huge effort over 8 years with a budget of about 30-40 million US dollars or euros, if you like, over these 8 years for research. And there we developed a basis for 40 innovations, and these innovations, they span from systems for remote maintenance and surveillance to optimized mooring systems to new generator concepts, but also greatly improved methods and tools to dimension floating and fixed offshore turbines. And the one innovation that has had the highest value were actually these models to optimize the constructions. And you can't say that is a game changer, but it has a huge impact on the cost of electricity from an offshore wind farm. If you can reduce the amount of steel with maybe 5%, then you have an automatic cost reduction also. And it's hard to do that with any sort of one type of innovation on the side. But I could mention a couple of fields of interesting research we're doing for a moment. One is to improve the operation of large wind farms. And today it is so that the wind turbines and the large wind farm, they operate independently of each other. They simply try to produce as much as possible at all times. And they don't really mind if they cause a damage for the neighbor turbine or not. They simply, each of them is optimized for themselves. I'm simplifying a bit now. What we try to do is to take a more holistic view and say, okay, if you operate this wind farm to maximize the total output power and to reduce the total loads on the turbines, that's the way you should operate the wind farms. And then it's not given that all turbines should operate at their maximum possible power output, but maybe some should reduce a bit so that others can produce more and so on, depending on the wind conditions and the state of the turbines and also on electricity price and other factors. So, and this kind of control systems you can of course implement to some extent already today, but the one big X factor is to figure out, okay, if I do something with one turbine in my wind farm, how will that affect the wind speed, and how will that affect then the power output of the neighboring turbines? And if you don't know that, you're sort of only guessing what is the optimized operation. So we are working hard to develop method that we in real time are able to predict how the wind speeds inside the wind farm is going to change depending on how we are controlling the individual turbines. And this I would say is one of the grand research challenges. Another sort of I would say a bit more engineering-like challenge is to combine the wind turbines with electrolyzers to produce hydrogen. And these concepts to do that offshore. You can imagine in the future maybe that you have wind farms floating far from the shore, out where you have the best wind resources, very remote locations, and you don't have a grid, but you're simply producing hydrogen, and then there can be a ship coming to pick up the hydrogen and transport it to wherever the hydrogen is needed. So this is a vision maybe for the future, I would say, when you need to produce not only electricity from wind farms, but also hydrogen to have an energy system with zero emissions of carbon dioxide.
Yeah, I can imagine that would really open up some resources that, you couldn't logically use with wires to transport electricity back to shore, but you could potentially generate hydrogen and bring that back to shore more easily and with less capital expense in the short term.
Yeah. And of course, another big research challenge is exactly how to bring the power to shore. In Europe, the vision for 2050 is to have 450 gigawatts of offshore wind installed. And this would supply 1/3 of the electricity consumption in Europe. And to have a grid system that is able to economically transport this electricity to shore and also have the power system to operate with this massive amount of wind power and still operating in a reliable and cost-efficient manner, it's also a great research challenge, I would say. And of course, if you look on the global potential for offshore wind, there is no sort of practical limitation, you could say, on the technical potential. It can supply maybe 18 times the global electricity demand. But if you look more to sort of what are the visions or scenarios for offshore wind development, 450 gigawatts in Europe for 2050. That's one of the most ambitious scenarios, and similarly for a global installation, it's between 1,000 and 1,400 gigawatts. These are the numbers that are sort of expressed by think tanks and similar bodies. And with these kind of massive amounts of offshore wind, it's really a challenge of how to develop the grid to bring the power to shore and the technology to do that. I would mention one more sort of research challenge, and that is apart from the first one I mentioned, how is the wind flow inside the wind farm? The other one I would say is the interaction between aerodynamics, hydrodynamics, the mechanical system, and the electrical system, and the interaction of this in these huge machines, 10, 20 megawatt machines, with wind spans of more than 200 meters, and in wind farms composing hundreds of such constructions. That is really a tremendous challenge to really be able to model and estimate the behavior in every detail. So this I would say is the second great challenge, and the third one is, as I said, the system science. So operating the power system with these massive amounts of wind power in the future.
Mm-hmm. Yeah, those are really interesting challenges and things to overcome. But I think certainly there are a lot of people working on it to make that happen. And those numbers you were quoting are quite extreme. You know, you're talking about a lot of offshore wind being brought into being used in Europe. That's really a great option for the renewable sector, I'd say.
Absolutely. So there is, with this, I think there is also great business opportunities. Of course, one is to develop and operate these large wind farms, and the other is to deliver service and technology to this huge, large market. And this market, I believe, will be at some stage being bigger than the oil and gas market that we have today for the supply industry. So this is a huge opportunity for new business. And of course, at SINTEF, we work with the industry to bring value to them and to solve the challenges that they see to optimize their services or technology.
Yeah, I think we're seeing a lot of oil and gas companies kind of move over into the renewable sector and take on these projects because they have that experience with their offshore platforms. Have you got any of them working with you at your research institute and helping develop some of these solutions?
Absolutely. So we've been working with a lot of oil and gas companies, and it is exactly as you say. They see that they have competence from working with large constructions offshore, and a lot of the competence that they have can also be utilized for offshore wind. Although you can say that when oil and gas one was on in the prime time, the profits were enormous. In offshore wind, I would say that profits are more long term, but they are still quite significant, and it's a good business opportunity and a long term business opportunity. And you also have the advantage that you will not, the wind will not stop blowing.
Mm-hmm. Well, thank you, John, for taking the time to talk with us and explain a lot of these developments that are taking place. I think it's great that, we as Americans from the United States, we're kind of capitalizing on all of the research that the Norwegians and the Europeans and UK, all of the work that's being done over there. So I think we have a lot to benefit from your work, and I appreciate you doing that. Do you see any U.S. companies coming and working with you and trying to gain some of the lessons learned?
Oh, absolutely. So we have a long tradition for collaboration with research centers in the U.S., in particular the National Renewable Energy Lab in Boulder, Colorado. They are even they are located in Colorado, they are actually quite good at offshore wind technology. So we very much appreciate collaborating with our colleagues there. And also American companies are very much present in the oil and gas business and also in the offshore business, and we see a lot of potential working together with them to expand also on the offshore wind business.
Well, is there anything else you'd like to touch on before we wrap this up? Otherwise, I think you've answered many of my questions.
No, I'm thinking good. So thank you again for having me at this podcast. I really appreciated it. Thank you.